Space, the final frontier. It's a vast, mysterious expanse that has fascinated humanity for centuries. From the twinkling stars to the distant planets, space represents the ultimate unknown. It's a realm of stars, planets, and the infinite unknown. A place where the laws of physics as we know them are put to the test, and where the boundaries of human exploration are constantly being pushed. But what happens when we fall back to Earth from that great expanse? What does it feel like to leave the serenity of space and return to the gravity-bound world we call home? Imagine stepping off a spaceship hundreds of miles above the planet. You're floating, weightless, with the curvature of the Earth stretching out below you. There's no ground rushing up at you, no sense of falling like you'd experience jumping from a building. Instead, you're suspended in a state of free fall, moving at the same speed as your spacecraft. Instead, there's just the silent black void of space and the shrinking Earth below. The vast emptiness surrounds you, and the only sound you hear is your own breathing. It's a slow, eerie descent at first, governed by the relentless pull of gravity. You begin to feel the subtle tug of Earth's gravitational embrace, drawing you closer with each passing moment. You might even feel peaceful, suspended in this cosmic ballet. The view is breathtaking, and for a moment you might forget the perilous journey ahead, but don't be fooled. This is no gentle float back to Earth. As you descend, the speed increases, and the once serene experience becomes a high-stakes plunge. As you get closer to Earth, things change dramatically. The planet that once seemed so distant now looms large, and the atmosphere begins to make its presence known. The atmosphere, so thin at extreme altitudes, starts to thicken. You can feel the resistance building, the air molecules colliding with your suit. And with that thickening atmosphere comes a force we're all familiar with on Earth, but amplified 1,000-fold in this scenario: friction. The heat builds up and the descent becomes a fiery re-entry, a testament to the power of Earth's atmosphere. We think of air as invisible and intangible, something we move through effortlessly. It's easy to forget that air is made up of countless molecules, each one playing a role in the environment we experience every day. When we walk, run, or even wave our hands, we barely notice the resistance because our movements are relatively slow. But at the speeds you'd reach falling from space, air becomes a wall. Imagine moving so fast that the air can't get out of your way quickly enough. The molecules pile up in front of you, creating a barrier that feels almost solid. This is why high-speed objects, like bullets or spacecraft, experience such intense resistance. This friction, generated by your body colliding with air molecules, creates an immense amount of heat. The faster you go, the more friction you encounter, and the hotter you become. It's a relentless cycle where speed and heat feed off each other, escalating to extreme levels. We're talking thousands of degrees Fahrenheit, hot enough to melt metal. To put it in perspective, the heat generated can easily surpass the melting point of many materials we consider strong and durable. Imagine the kind of temperatures that can turn solid metal into a glowing, molten liquid. This is the same principle that causes spacecraft to heat up during re-entry. As they plummet back to Earth, they encounter the thickening atmosphere at incredible speeds, leading to intense friction and heat. The spacecraft's surface glows brightly, not because it's on fire, but because of the sheer thermal energy being generated. They're not on fire in the traditional sense, but glowing from the intense heat of atmospheric friction. This glow is a visible sign of the energy being transferred from the air to the spacecraft, a testament to the harsh conditions of re-entry. This is why spacecraft need special heat shields designed to ablate or burn away in a controlled manner, carrying the heat away from the craft itself. These shields are engineered to withstand the extreme temperatures and protect the delicate instruments and crew inside. Now imagine that heat surrounding you with no protective shield. The human body is incredibly resilient, but it has its limits. Without protection, the intense heat would be unbearable, leading to severe burns or worse. It's a sobering thought and a stark reminder of the unforgiving nature of our atmosphere when it comes to high-speed entry. The very air that sustains us can become a deadly adversary under the right conditions. But heat isn't the only factor at play in this deadly descent. The combination of speed, friction, and atmospheric pressure creates a complex and dangerous environment that requires careful planning and engineering to navigate safely. You might be thinking, if I'm falling from that high up, I'll hit the ground at an unimaginable speed. It's a common fear, imagining yourself plummeting uncontrollably towards Earth, much like a meteor streaking through the sky. But the reality is quite different. While it's true that you'll accelerate due to gravity, there's a limit to how fast you'll go. This limit is not just a theoretical concept but a very real phenomenon that affects everything falling through the atmosphere. That limit is called terminal velocity. Terminal velocity is the maximum speed an object reaches during free fall, and it's determined by a balance of forces. Terminal velocity is the maximum speed an object reaches during free fall. When an object falls, gravity pulls it downward, but air resistance pushes upward against it. It occurs when the force of air resistance pushing upward against the falling object equals the force of gravity pulling it down. Think of a skydiver. Initially, they accelerate rapidly. As they fall faster, the air resistance increases. But as air resistance increases, their acceleration slows down until they reach a steady speed, their terminal velocity. This balance of forces ensures that they won't continue to accelerate indefinitely. In the thin upper atmosphere, your terminal velocity would be incredibly high. The lack of dense air means less resistance, allowing for higher speeds. But as you fall into denser air, that velocity decreases dramatically. The increasing air density provides more resistance, slowing you down significantly. While still dangerous, it's far less than the speed of a meteor, which burns up due to atmospheric friction. Meteors travel at tens of thousands of miles per hour, encountering extreme resistance that causes them to heat up and often disintegrate before reaching the ground. In contrast, a human falling from the edge of space would reach a much safer terminal velocity, thanks to the protective cushion of our atmosphere. So, can you survive a fall from space? The answer, like many things in science, is, it depends. Your survival hinges on several factors, the most important being altitude. If you're talking about a fall from the International Space Station's orbit, roughly 250 miles above Earth, your odds are slim to none. The heat from atmospheric friction at that altitude, even with a specialized suit, would likely be fatal. But what about a fall from a lower altitude, say, the edge of space, commonly defined as 62 miles above Earth? Now things get a bit more interesting. While still extremely dangerous, survival at this altitude isn't entirely out of the question. There have been remarkable cases of people surviving falls from incredible heights within the Earth's atmosphere, demonstrating the resilience of the human body and a bit of luck. Section 5. Suit up. When clothes make the difference between life and death. Let's talk about gear. A regular spacesuit designed for the vacuum of space wouldn't cut it for atmospheric re-entry. You'd need a suit specifically engineered to withstand the extreme heat and forces involved. Such a suit would need to be incredibly heat-resistant, potentially incorporating materials like those used in spacecraft heat shields. It would also need to be aerodynamic, minimizing drag and helping to control your descent. Imagine a suit with wingsuit-like features, allowing you to glide and maneuver through the atmosphere. Remember, this is all theoretical. While current spacesuits offer some protection against the harsh conditions of space, nothing exists right now designed for a safe solo descent through Earth's atmosphere. Section 6. Beyond the spacesuit experimental tech for a safer fall. Beyond specialized suits, scientists and engineers are exploring other technologies to improve the odds of surviving a fall from space. One concept involves inflatable heat shields that deploy during re-entry, creating a protective barrier around the falling object or person. Another idea involves using magnetic fields to create drag and slow the descent, reducing the heat generated by friction. While still in the early stages of development, these concepts highlight the ingenuity being applied to solve this complex problem. It's important to note that these are just a few examples of the ongoing research. The quest to conquer the challenges of space travel and return constantly pushes the boundaries of our technological capabilities. Section 7. Lucky Stars. Tales of survival against the odds. While a fall from space is an extreme scenario, history is filled with astonishing stories of human survival against incredible odds. Take for instance the remarkable case of Joseph Kittinger, a U.S. Air Force pilot who in 1960 jumped from a balloon at an altitude of 102,800 feet, almost 20 miles. While not quite space, this daring feat exposed him to extreme conditions, and he survived. His experience provided invaluable data about high-altitude jumps and the human body's response to extreme environments. While his jump doesn't directly compare to falling from space, it underscores the human spirit of exploration and our ability to push beyond perceived limits. Section 8. The human drive, pushing boundaries, one fall at a time. Kittinger's story, like many tales of survival, speaks to a fundamental aspect of our nature, the drive to explore the unknown, even when it's dangerous. It's this same drive that has led us to climb the highest mountains, dive to the deepest trenches of the ocean, and yes, even venture into the vastness of space. Each daring feat, each test of human limits, expands our understanding of ourselves and the universe we inhabit. Every calculated risk, every daring leap into the unknown yields valuable knowledge that propels us forward. So, while the question of surviving a fall from space remains a complex one, it's a testament to human ingenuity that we're even asking it. Section 9. What goes up? A final thought on exploration and return. As we continue to explore space, the challenge of safely returning to Earth from those journeys will remain paramount. It's a challenge that will continue to push the limits of our technology, our understanding of physics, and our courage. But one thing is certain, the human spirit of exploration will never be grounded. We'll keep reaching for the stars, knowing that with each daring leap we learn, we adapt, and we push the boundaries of what's possible. The journey back to Earth might be perilous, but the knowledge and wonder we gain from exploring the cosmos make the journey worthwhile.